Good morning, everyone. I'm Cindy Csigoy, Executive Director of the Cleveland 2030 District. Glad to have you with us today. We've got a great presentation today. As you know, the Building Education Series is presented by all of those organizations on the screen. Cleveland 2030 District partners with one of these organizations for each of our sessions. And so thanks very much today to our partners at U.S. Green Building Council. They're our partner for today's session. Today's session, of course, is the Building Envelope's Impact on Efficiency. We've got a great panel of speakers with us today. We're really going to dive into this subject and really learn more about how Building Envelope can really improve building efficiency if you're doing all the things that all of our speakers are going to tell us to do. Special thanks to our sponsor today, AeroSeal, one of our newest professional partners to the Cleveland 2030 District. We appreciate their support. AeroSeal provides computer-controlled, aerosol-based duct sealing technology and airside HVAC solutions that improve indoor air quality and comfort and increase energy efficiency in buildings. AeroSeal simply and quickly resolves airflow and exhaust issues and brings buildings up to code, regardless of age, scope, or size. Results are instant and measurable, with buildings achieving improved air quality and code compliance immediately and increased efficiency and energy savings within the first month. Thanks again to AeroSeal. This is our list of sessions for 2023. This is the second one, of course, and we've got a great lineup for the year, so please mark your calendars. I'm going to give a shameless plug to our Green Building Challenge. We closed that out last night, and our judges will be reviewing the entries, so stay tuned. We'll be announcing those winners within the next couple of weeks. Before we start, we are providing continuing education credits for today's session. Please, I'll send out a Google sign-in sheet. Please complete it by close of business today. We're also going to send out a very short survey. Please complete by close of business today. This is just to make sure that we're on track providing sessions that are of interest and of value to you. Please use the chat feature to ask your questions. We're going to hold questions to the end of the presentations. And we'll address them in panel style. And today's session is being recorded, and you can find it in another day or two under District Library on the Cleveland 2030 District website. I'm not going to read through these bios so that we save time for presentation, but these were provided to you ahead of time. Our first speaker will be Dave Finley from Garland. Then we'll move to Helen Sanders and Alexandra Blakesley from Technoform, followed by Julianne Geyer from Garland. And John Stahl will wrap it up from Preferred Solutions. And so I'm going to stop sharing and I'm going to turn it over to Dave.
All right, thank you, Cindy.
Thanks, Dave. Your presentation is up. You're good to go.
Perfect. All right. So before we begin, I want to express my gratitude to the Cleveland 2030 District for putting on this seminar, as well as inviting me to speak to you today. I'm going to start us off with an overview of energy efficiency in the building enclosure and how to get the most bang for your buck, or that Goldilocks sweet spot, as it relates to insulation and air leakage, as well as the moisture impacts that these materials bring to your enclosure assemblies. I'm sure that everyone attending today knows that the enclosure consists of the 6 sides of the building that separates the indoor environment from the exterior environment. But that separation needs to control bulk water entry, air leakage, condensation development, and thermal conduction via insulation. There are other enclosure control layers but these are the ones that we primarily focus on, and I listed them in order of importance. You'll notice that I mentioned insulation dead last, and yet the industry started off with a myopic obsession with insulation, and unfortunately, we still do. When it comes to reducing energy use, as well as moisture problems, air leakage is the more important control layer in that scenario, and I'll go over why in this portion of the seminar. Buildings in the United States use a big piece of the pie when it comes to total energy use. So it's no surprise that the industry responded with adding insulation. Of course, we started adding a lot of insulation without fully understanding the hydrothermal implications of its inclusion in our enclosure assemblies, and most notably, air leakage. So the effects of insulation, for example, here we have an infrared thermograph showing the gradual thermal gradient across an uninsulated wall assembly, consisting of a steel stud framing and brick masonry cladding. Under these conditions, with the exterior at 0 degrees and the interior at 72, the back side of the exterior sheathing is about 33. And for comparison, the dew point of most unhumidified commercial buildings ranges from about 25 to 38. So the amount of condensation related to air leakage or convection and vapor diffusion in this condition is pretty limited. Whereas now let's look at the same wall and add bad insulation between the studs. You'll notice right away that the thermal gradient is markedly different, and that the metal studs now have a significant influence with thermal bridging, which is what you would notice when scanning your walls with an infrared camera, as shown here. Now that the temperature at the studs is warmer than before, it's now 41 degrees, and the sheathing temperature is now 14.6. Now the sheathing temperature in the middle of the stud cavity is well below the dew point range of most unhumidified commercial buildings, and it's below freezing, which means frost can now develop on the back of your sheathing. And if you don't believe me, here's a perfect example. You can see the frost buildup on the sheathing in the photo to the left, but at the studs, the condensation is actually occurring on a warmer surface. So it's actually liquid water, as seen with the water indicating paper on the right. Now, eventually that condensation developed as frost will thaw and either wet the insulation, which could lead to mold, or drain down into the stud track and either cause corrosion of that track, or even manifest itself as a leak on the floor in your building. None of this is desired in our buildings, and for a while, the industry tried to tackle this problem with vapor retarders, but the same and new issues cropped up. So the next solution to our woes was, of course, let's just add more insulation. But now it's in the form of continuous insulation. The insulation lobby at ASHRAE 90.1 must be buying voting members new cars or something to have such a monomaniacal approach to energy efficiency and moisture control. But this time, as I mentioned, the insulation is now placed on the exterior side of the sheathing, which is where it belonged in the first place. And it will be continuous to limit the thermal bridging effect of those studs and warm the backside of the sheathing above the dew point. And this concept has given rise to several proprietary products to accomplish this code mandate. But in order for this to work, a specific amount of continuous insulation is needed to accomplish the goal of getting that sheathing temperature above the dew point. This is termed the insulation ratio. And I know there's math on the screen and it's early in the morning, but rest assured the code does this for you. There is a reason why the prescriptive R values for walls have not changed and why they are what they are. If you calculate the insulation ratio for our climate zone, we get 0.37. But what does that mean? Well, if you look at it with exterior temperatures and interior dew points, the green cells are below the 0.37, which means that condensation will not develop on the sheathing in these cells when it falls in that range for those exterior temperatures for our climates, as well as interior dew points for thermal comfort. Now, many designers will opt to use R19 or even R21 in lieu of R13 because more is better, right? Well, it's not, because now you have pushed the 0.37 into the red cells, which means condensation can develop. Therefore, it is important to only use the prescriptive insulation ratio and not deviate. More continuous insulation is better than more bad. Technically, we want only continuous insulation on the exterior, but sometimes that's not feasible, particularly with retrofitting existing buildings. We have a larger stock of existing buildings, many of which do not have insulation or a minimal amount. Some renovation products may require you to include insulation to bring your facility up to current code, or you may want to just add insulation as part of your 2030 goals. Well, a lot can go wrong if you add too much, use the wrong type, or even install it in the wrong place. Let's start with an older mass masonry wall, which we have a lot of stock of here in Cleveland, that you may want to add insulation to the interior and frame out a new wall. What does that do to the hygrothermal behavior of that wall? The uninsulated version of the wall on the left has a very gradual thermal gradient across the wall, similar to that uninsulated stud wall from earlier. Well, you notice that the only width of brick that's below freezing is the outer width, which limits the potential for freeze thaw issues. And typically that face brick are of better quality and can resist freeze thaw damage much better. However, by adding insulation, which reduces the thermal energy transferring across the wall, everything outboard of the insulation will now be much colder, to the point that, as seen on the right, the entire brick wall is now below freezing, which means that every width can experience freeze thaw damage, especially the inner wides, which typically use lesser quality materials. This can lead to both unsightly damage or structural damage of your existing masonry walls. Now, these are a few examples of freeze thaw damage that occurred because too much insulation was added. The image on the right had damage to the inner wides as well, which resulted in significant repairs. Another issue with insulating a mass masonry wall, or even precast concrete walls for that matter, is the location of the insulation. Many will frame out a new wall and place bad insulation within the stud framing, while bad insulation is air permeable. So interior air that leaks into that airspace created between the framed wall and the existing masonry wall can condense on that cold surface. Some of this condensate will be absorbed into the masonry, which can further exacerbate that freeze thaw issue. But some of this water can eventually pool on the floor and eventually manifest itself in a leak when it's just condensation. Therefore, the best approach to insulating a mass masonry wall or precast is to use closed cell spray foam that directly adheres to the back of the existing wall. And this removes air spaces for convective condensation to occur, as well as provide the continuous insulation without thermal bridging. Now, the thickness of the foam must be evaluated to make sure that other issues will not be created. ASHRAE 160, which I'm a voting member of, is working on design criteria for this very subject, to which I'm the co-chair of the task force to develop that criteria and language. And this should be out soon. Another approach is to put the insulation on the outside where it belongs. One method is to overclad with a rain screen concept. This approach applies a weather-resistive air barrier to the existing wall, along with mineral wool insulation, a vented hat channel, framing that these metal panels or other cladding materials can be attached to. And if you're looking for a facelift for your building, this is certainly the way to go. Another option is EIFS. Now, EIFS gets a bad rep due to the issues found in the 90s. But since that debacle, the EIFS industry has the most stringent tests that need to be passed than any other material in the market. So just like anything else, it is installed right, it is completely suitable. Now, this concept is actually all the rage in New York City right now as they attempt to energy retrofit their existing buildings, as well as remove issues with facade ordinances. So this is not something that should be scoffed at all. But similar to the metal panels, a water resistive air barrier is applied to the wall, as seen in the upper right. Then expanded polystyrene insulation is adhered to that to create a drainage plane. And then the EIFS lamina, which consists of a reinforced base coat and a finish coat, which nowadays can be applied to even look like brick, stone, wood, even metal. It can be pretty much anything nowadays. They do some pretty amazing stuff. But it should be noted that the EIFS is the only product really that effectively achieves a true continuous insulation, as there's no thermal bridging associated with any fasteners or framing. There is a minor decrease in R value due to that drainage plane, but that's a deeper technical discussion, but it's so small, it's pretty negligible. On the left here is a rendering of the EIFS assembly, which with that brick finish that I mentioned. And on the right is a rain screen concept with the mineral wool, but here beneath a terracotta cladding. Now, which of these would you think has more embodied carbon? Well, it's actually the mineral wool, and it's because of the mining and manufacturing that must go into making that mineral wool. So again, EIFS is a viable overcladding possibility, and it can reduce your embodied carbon. You'll hear other products today that can reduce the embodied carbon aspect of your building materials, which is the latest trend in sustainability, as well as where ASHRAE is going. All right, so gone through all the do's and don'ts of insulation, but here's the real truth as to why it's the least important. This is something that the insulation lobby does not want you to know, but there is diminishing returns on the amount of energy saved as you increase R value. In fact, for every doubling of R value, you only get half the reduction in energy use. Now, as mentioned before, the R values have maintained pretty close to the sweet spot for walls for issues that we discussed already. Windows and doors have technology now that you'll hear about today that can significantly move that needle closer to the sweet spot. But unfortunately, the R value for roofs continues to increase with the code, mainly because of the trade-off option, but also it can be added without much moisture problems. However, it's already on the flattened part of the curve, so increasing this value only adds more cost to you with little return on investment from energy savings. So here's a little example. The cost for insulating per R value and per square foot are listed here, with polyiso, which is the major roofing insulation, as the most expensive. If you decided to increase your roof insulation from R20 to R30, well, based on the curve, that would save you a little over 1 BTU per hour per square foot for a total savings of 70 cents per square foot. Well, based on average gas prices for Cleveland, the cost per square foot for a R10 increase is $3 per square foot. So you're starting off in the hole $2.30 per square foot. The ROI will take a while if we focus on insulation only. In true American fashion, it's time to root for the underdog, which is air leakage. It is starting to get its day with ABA and the codes, but it is second in importance, but usually overlooked, and I have no idea why. For starters, few, if any of us, have ever been in a building and felt chilly because there isn't enough insulation or the ambient temperature is too cold. it's usually because of a draft. Whether you're sitting near a diffuser or draft from an air leaky window, or even from the thermal radiation you feel from poor glass or unthermally broken window frames, it's usually airflow that causes thermal comfort issues. And it's usually on the neck or the feet. And it most certainly causes the most moisture and energy problems. So we need to understand and control air more than we do conduction via insulation. Now, in order for air leakage to occur, we need two things: a pressure differential and a path. For buildings, the pressure differential is primarily created via either wind pressure, buoyancy, or stack effects, or pressure created by the mechanical system itself. But it can't be taken singularly. When they act on the building simultaneously in an additive or subtractive way, with the extremes shown here. When taken together, you can see the roof to wall condition and the wall to foundation can have the most pressure differential than the rest of the building, which is not surprising, as most of the moisture and energy issues also occur at those locations. The second aspect needed is a leakage path. There are two types of paths to be concerned about. The first is an energy leak. Here, the energy flows directly from in to out, and it flows over and warms all the surfaces that it touches. And so moisture doesn't leave the system here, but it's just complete heat loss. Conversely, there's a moisture leak, which is shown there on the right. Here, the airflow is circuitous, such that as it flows, it loses energy. And so that air can now touch a surface that's colder and cause condensation development. This can lead to mold growth, corrosion of your framing, as well as structural degradation of your sheathings. This leakage path is equally bad, if not more so, than the energy leak. So obviously controlling air is a major focal point behind controlling bulk water. But here are all the things that we need to control across our assemblies. But some are indirectly controlled by some of the things that we use. But if you look closely, the air barrier has an effect on all of them. So how does air leakage stack up against insulation for energy use? Well, significantly better, as it's a linear or a one-to-one relationship. So that every CFM per square foot you choke off, you reduce 1 BTU per hour per square foot of energy use. Now, the cost of air sealing will typically consist of a whole building air leakage test to determine the current energy use, as well as using other tools to find those air leakage sites. Once those repairs are made, oftentimes it can be done actually during the test. The building is retested to confirm the new rate. And depending on the size of the building and how many leaks are found, you can expect about a $10,000 to $20,000 range for doing all of that. And the process takes about a week to complete, assuming that there's nothing too crazy that needs to be repaired. But with this approach taken, you can reduce air leakage from the 0.4, which is the code maximum, to say 0.1 CFM per square foot, and you would reduce your monthly energy usage by 84,000 BTUs per square foot. Now that is a much, much better ROI than adding insulation. Now, for those of you that are unfamiliar with the whole building air leakage test, it generally consists of a blower door or several, depending on the size of the building, to induce the positive and negative pressures. If your mechanical system is strong enough, you can actually use that in lieu of the blower doors. But during the test, we can use smoke generators like the top right photo, or even infrared thermography, which is the bottom right, to locate the leakage paths. For small leaks, typically we'll use sealant and spray foam to choke off those paths. But for larger repairs, we'll have to stop the test, allow a contractor to make those repairs, and then retest. So the energy loss for both insulation and air leakage is shown here. The graphs are combined. Now the code provides a U value of 0.064 for our climate zone. And the maximum air leakage rate I mentioned is 0.4. That means that the code compliant energy loss, this is what the code allows you to lose, is 34.5 BTUs per hour per square foot. That's a lot. And a major portion of it is from air leakage. So what do we do within our district as well as moving forward? Well, to summarize and conclude, I recommend that we shoot for the Goldilocks zone for our enclosures. Not too little, not too much, but just right. Our walls and roofs are on the too much side from a cost benefit ratio standpoint. The fenestration is trending to move into the sweet spot, and you'll hear about that next. But air leakage is way too far out from the sweet spot, even with the proposed reduction of the 0.4 to 0.35, and even possibly 0.25 in the codes. I'd like to see us strive for 0.2 or less, where the air leakage crosses the insulation curve in an almost supply and demand curve equilibrium. It is here where the cost of implementation is worth the energy savings to achieve a good ROI, along with reducing the energy uses of our existing buildings. With that, you said that we're saving questions, so I'll turn it over to Alexandra and Helen.
Thank you, Dave. That was a great presentation. Yes, we will hold questions to the end, but type them in the chat, and we'll turn it over to Helen and Alexandra.
Hi, can you see my screen?
Yep, you're good to go.
Okay, great. So Alex and I are going to be focusing on fenestration. But before we dive into that, I wanted to talk a little bit about the current status of building decarbonization and why why windows matter so much. So let's talk a little bit about decarbonization. So the UN Environment Programme issued their status report for buildings back in November alongside the COP27. And they concluded that the building segment was not on track for the decarbonization transition. And they said specifically, it's not making the deep systemic changes that are needed to get on that trajectory. But what it did say was that we already have the technologies to close the gap. It's not a technology issue. It's about the fact that we really need to deploy the technologies that we have, and we'll talk about that a little later. When we look to the US, even the US is not on track for decarbonization. Our building codes are not on track. Here is the energy use index of ASHRAE 90.1 over the last few decades. You can see the stringency is getting better, but we're not on track to where we need to be for the interim 2030 net zero energy goals. And not only that, but the adoption of those energy codes is lagging. There are great swaths of the country that are many versions behind the current model codes. And this is a map from the Department of Energy showing the statewide adoption. And I highlight Ohio here. It is still on 2010 version of 90.1, and DOE have assessed it as being 35% less efficient than the 2019 version of 90.1. And just for future reference, when Alex talks about fenestration, the fixed fenestration requirement maximum is a U factor of 0.45 in IP units. That compares to the 2019 version value of 0.36 in this climate zone. And in addition, the emission limits are actually being now set for existing buildings. So there are many jurisdictions, and here's a map of the jurisdictions that have signed up for the building performance standards program that was launched by the Biden administration recently. These jurisdictions have committed to providing or to having policies for greenhouse gas emission targets for their buildings by Earth Day 2024. And why do I mention this? Really for two reasons. One is that that's going to make it's going to drive existing buildings to retrofit their facades. And secondly, there's a little gap or a tension that's going to be created between the baseline codes and these emission targets for existing buildings. Because if your existing codes can't build you a building that's going to meet the emission standards, you're going to have a problem with new existing buildings, and you'll have to start retrofitting them pretty early on, so they won't be future-proofed. So let's talk a little bit about why windows matter. So the DOE have identified windows as being responsible for about 40% of energy use in buildings. And there are 2.4 million commercial buildings that have single pane glass in them currently, and non-thermally broken framing systems. That's 40% of all existing buildings in North America. That's huge. They've also identified what you need, what they characterize as a net zero energy window. And it's not that extraordinary. We have the technology already. It's a thermal performance of R5, which is a U of 0.20. It requires dynamic solar control, which is either adding a automated exterior shading system to a high performance solar control coating, or using dynamic glass, sometimes called electrochromic or EC glass, and then combining that with lighting controls for daylight harvesting, and then energy harvesting through PV, and together you have a net zero energy window. If we replaced every window in the United States, every commercial window in the United States, we would turn an energy usage of $20 billion into a net energy saving of $15 billion. It would be a net surplus of energy because of the energy harvesting. The other thing I wanted to just talk about is the decarbonization strategy for buildings. We have to get to decarbonization in 30 years, less than that now. And the strategy in buildings is electrification, and that means replacing gas furnaces with heat pumps. You probably heard a lot about heat pumps right now. The challenge with implementing heat pumps is with poor envelopes, you end up with two issues. One is it's a huge load and you have to have a lot of heat pump capacity to manage that. And it shifts the peak loads in the building from the summer to the winter, and not just to the winter, but the winter hours in the morning, which is puts a lot of stress on a renewable grid, because maybe solar and wind aren't necessarily available at that time of the day. So really what it points to is a high efficiency envelope to help enable the heat pump implementation and electrification of buildings. So I'm going to hand over to Alex right now, and she's going to talk about some of the fenestration technologies that are actually available that can be implemented today to get to that net zero energy window.
Hi, everyone. Nice to be here. So as Helen said, I'm going to talk about the technologies, show some case studies. But first, I just want to kind of talk about some of the details of what happens in the window edge. So 85% of heat transfer in windows occurs at the edge. Primarily, that's through conduction. If you look at kind of this top, can you just click one, Helen? I think there might be some animation.
There you go. Oh, sorry.
So at the top here, you see the spacers that are inside of the insulated glass unit. And then underneath the framing system, within the framing system, you see polyamide strips, which we'll talk about a little bit later. So primarily heat transfer occurs through conduction. That's where 50% of the energy flow occurs. And then you start working on addressing convection, radiation through some of these more advanced thermal barriers that are underneath the framing system. Next. So why is that really important? Heat flows like water or like electricity. It always goes path of least resistance. So What I'm going to talk about first is the polyamide strips, the thermal barriers, because that's really the first place you have to start to improve your overall window U factor. And then we will talk a little bit about the edge of glass. So those two kind of really have to work in tandem because they're a system. So we use this example just to kind of put in perspective of what happens when you want to improve your window and how does that have an effect on the overall envelope performance. So we started with 50-50 window wall ratio with an effective R value of 3.6. And then you have options. You can either improve the wall or you can improve the windows or maybe both. So we took an example of starting with a really well insulated wall of R40 and a pretty poor window performance, and your effective R value doesn't change by much, it just increases by 0.2. But if we improve the window performance, even with an R20 wall, those can work in tandem to really improve that R factor by a factor of almost 2. So as I mentioned, I'll talk a little bit about the polyamide thermal barriers first, because you really have to, when we get into the details of the window edge, that's the first place that you want to start. This just basically shows the innovation history. These started back in the late 70s with really small thermal barriers to really address that conduction. So moving away from like a non-thermally broken aluminum frame and then adding that thermal barrier in to address conduction. And then those just kept increasing in size. And then eventually in the kind of late 80s, 90s, we have more complex shapes to start addressing convection. And then finally, some more advanced technologies to manage radiation. And then there's other technologies that started being implemented and applied to different applications, such as replacing aluminum pressure plates with a polyamide pressure plate. So this is just kind of giving you a sense of where we're at in the US. Northern Europe is basically well ahead of us, kind of using the 90s to 2000s technology. Canada is just behind them, and US, this is really business as usual for us, these smaller thermal barriers. Sometimes more complex shapes get used, you know, in larger kind of projects, but this is kind of where we're at right now. But as Helen said, the technology is already available. So if you look at this, this is just a typical business as usual window assembly. This has a U factor of 0.38 imperial units. This is really even beyond some of what the code requires. So in Ohio, for example, for following a 2010 compliance path, a system with a much smaller thermal barrier would be meeting code. But as Helen mentioned, that doesn't really get us to where we need to go for net zero. So we want to try to move towards these more thermally efficient systems. So R5, an R5 window is kind of the best in class. This is part of the Department of Energy's net zero window solution. This is just one example from Wasa Window and Walls, but there's also several other manufacturers that make R5 performance windows, and you can get down to a 0.16 U factor with this type of system. So next, I'll just kind of go through some case studies to give you a sense of how some of these technologies are used, and then also talk a little bit more about once you improve the frame, how you can then improve the edge of glass to get some additional thermal performance. So this is a project in Ithaca, New York. They were using a larger thermal barrier and had kind of a complex shape here with a bellow shape to allow for vertical movement. And then it kind of is also working not just for thermal performance, but also for structural requirements. Another easy way to improve thermal performance, and this is more for curtain wall applications, is by introducing a pressure plate, changing it from an aluminum pressure plate to polyamide. And this can improve the curtain wall U factor by up to 20%, and then also can address some condensation resistance and again, some structural challenges. This project, they were at Georgia State University College of Law. They had a goal of getting LEED Silver certification. So they were really had to have technologies that could help them meet more current energy codes. And so they selected a larger polyamide thermal barrier and a 2-inch pressure plate in the curtain wall to achieve that goal. And so next we'll talk about, once we improve the frame, now we can move on to the spacers inside of the insulated glass unit. Warm edge spacers are a good technology that can basically improve and eke out a little bit more thermal performance in the insulated glass unit, and also improve the overall window U factor by 0.02 to 0.03. This can really help, like Ohio is kind of in that, in that later or older code compliance path. But if you're trying to go above code and trying to go to net zero, this really works well in tandem with the improved frame performance. It has a 25-year track record, and the durability really comes from the solid metal back. So you get that performance. It's kind of like a similar concept to thermal barriers. You're breaking the thermal heat transfer through conduction by using a hybrid plastic with stainless steel. So you get the durability of stainless steel without sacrificing the thermal performance. One important note is for really all of these technologies is they have to be specified. So code, only takes us so far. And if we want to go above code, it's good to kind of know the details of how all of these components are working together, because it can really make a huge impact on condensation performance, thermal performance, and otherwise. This is a really, really cool project. The Space Needle project, basically they had a lot of design challenges that they were trying to achieve. So they were trying to reach LEED Gold, retain the current chiller size, and then also increase the glass area by 200% while still maintaining the look and feel of the original Space Needle. And so the hybrid plastic stainless steel warm edge spacer is really key to that. It allowed them to kind of meet both the thermal targets that they were trying to do, and then also meet the structural needs. They had some structural members that didn't have a thermal break, so the windows and the glazing had to really work extra to make up for that. And so what was kind of cool about this project is that you also see the warm edge spacer being used in an unsupported edge condition, and you get those really nice views of out over the Pacific and Seattle. So next I'll just talk a little bit about retrofit technologies. These are some other strategies that can be used beyond just the retrofitting with an IGU and the framing system. There's some additional technologies where you can actually add on to the existing window system. So there's a company called InnovUse that makes retrofit assembly that basically can either be added on the exterior or the interior. The main advantage is the exterior, because you can basically create a vapor tight seal and also have a desiccated thermal cavity between the original and the new added glass. So it almost kind of creates the basically an IGU on the external side. And then there's also another technology that's more for the interior, where you can add secondary glazing and do thin glass. This is made by a company called Alpin. The advantages of some of these technologies is they really reduce the cost of window replacement, and also kind of gets around some of that red tape, because you don't necessarily need to go through the full installation process and still improve the thermal performance. And with that, I will pass it back to Helen to talk a little bit about the Inflation Reduction Act.
Great. Yes. So Cindy asked us to talk a little bit about the IRA. I like to think of codes and standards and incentive policies as carrots and sticks. We talked a lot about the sticks, i.e. the baseline codes, but we really need carrots to incentivize the market to go above code. And the Inflation Reduction Act actually has a lot of carrots that can really help that. The first part of the Inflation Reduction Act that I want to cover is the incentives for states and local jurisdictions to accelerate the adoption of building codes. There's $1 billion, about a third of it is tagged for the adoption of the newest model codes, and 2/3 of it, though, is for the adoption of net zero codes. There's actually a voluntary appendix already in IECC 2021. So that's good. That hopefully should move that map into a place that looks better than it does now. The second thing I want to talk about is the changes to the 179 energy efficient building tax deduction. Basically, this tax deduction is making it easier to access that credit. It's a tax deduction for building owners installing efficient lighting, envelope HVAC systems. The reason that it's making it more accessible is it's lowering the threshold for qualification down to 25% of energy savings above a baseline. And also changing the amount of credit that you get per square foot of floor area. Previously, it was a flat rate of $1.88 per square foot. Now there's a sliding scale, and there's a multiplier on that sliding scale if you meet prevailing wage and apprenticeship standards in the construction of the building. So now you can have a tax. The tax credit is from about half a dollar a square foot all the way up to $5 a square foot. You can use it every 3 years as a building owner. And also a really neat thing is they've now allowed all tax exempt entities to transfer that credit to the designer. The designer of the building is likely to be not tax exempt. And so that can actually, of course, save money overall for the building owner. The other neat thing is that there's a retrofit program that's now been established. So the biggest issue, I think, as Dave talked about, is the existing buildings. And so this allows the cost of retrofits to come down, which is a real key for window replacements, because they tend to be pretty expensive. And so with that, I would like to, close up. And just to conclude, we have the fenestration technologies to do what we need to do to get to net zero. The recommendations here, though, we have to specify above code performance, especially in Ohio, since we're so far behind where the model codes are now. And the model codes now are still don't reflect the technology that's available in the market. We have easily specified technologies that can meet those net zero energy targets. We have complex polyamide thermal barriers that's available and other components. We have durable warm edge spacer, and then we have lots of advanced glazing infills. We don't have a lot of time to dig into that, but there are triple panes, there's vacuum glazing, there's dynamic glazing. There's a lot of center of glass technologies. And then we also have retrofit strategies that we talked about. We have the full fenestration and envelope retrofit that will give you the highest performance, and maybe you can use the tax credits to get there to make it more cost effective. And then also we have those interior and exterior secondary glazing options that we just talked about. One thing I didn't mention on the IRA, there's also a tax credit for implementation of dynamic glazing, electrochromic glazing. If anyone wants to have any details of that, they can contact us afterwards. And with that, I will hand over to our next speaker.
Thank you so much. That was a wonderful presentation. And I love that mantra. We have the technology. That's been the 2030 district message for years. So yep. I really appreciate that. Let's turn it over to Julie. Thank you, Helen and Alex.
Thank you.
So we were having a little technical difficulty. Julie, if you need me to step in with your slides, just let me know.
Okay, can you hear me okay?
Yes, and
Oh, great.
your slides look good. Thank you.
They're on. Okay, great. Thank you so much. Yes, thanks for having me today. I'm excited to take you through some technologies in the building products and roofing space that can help you reduce your carbon footprint and focus on your sustainability efforts. So go ahead and dive in. Many of the subsequent slides that I have here today reference cool roofing and the different technologies that you can use to achieve a cool roof. So I want to take some time to give a little background on cool roofing and what that means. A cool roof is one that strongly reflects sunlight, also known as solar energy, and also cools itself by efficiently emitting any heat that was absorbed. The cool roof stays cooler and reduces the amount of heat conducted into the building below. So, for example, if a building doesn't have any air conditioning, this will keep the building cooler and will reside at a more constant temperature, again, keeping the internal temperature of your building lower. The Cool Roof Rating Council, CRRC, is a nonprofit organization who maintains a credible and unbiased third-party rating program for measuring and reporting the radiant properties of roof surfaces. So manufacturers can submit their products to the CRRC in order to substantiate their cool roofing claims. So the CRRC will then publish the measured solar reflectance and thermal emittance values on their products directory site, which is a public site that anyone can go to. You'll also find on product labels this CRRC reference logo box with those values posted. These solar property values are measured via ASTM standards, such as the ones I have listed here, ASTM E1980, C1371, and C1549. These test methods are utilized by independent accredited third-party labs and not by manufacturers. So to, again, substantiate claims, the solar reflectance is defined as the fraction of solar energy that's reflected by a roof, and the thermal emittance is defined as the relative ability of the roof surface to radiate heat. So a product's initial values are posted, and after those initial testing, the product sample will be sent to an approved test farm where it's exposed for outdoor weathering for 3 years. So that outdoor exposure will occur in 3 different designated locations in the United States that collectively represents the US average. So those areas are Arizona, which is viewed as hot and dry, Ohio, cold and temperate, and Florida, which is hot and humid. So after those 3 years of exposure, the weathered specimens are then sent back to an independent lab to get those solar reflectance and thermal emittance values sent back. The 2 basic characteristics that determine the coolness of a roof are the those solar reflectance and thermal emittance values. Both properties are measured on a scale from 0 to 1, where 1 is 100% reflective or emissive. So one way to measure how cool a roof can be is then by calculating the solar reflectance index, the SRI. SRI is an indicator of the ability of a roof surface to then return the solar energy back to the atmosphere. Roofing material surfaces with a higher SRI will be cooler than surfaces with a lower SRI under the same solar energy exposure, especially when looked at on a sunny day. So as mentioned on the previous slide, using materials with higher SRI values can enhance building occupancy comfort and reduce your air conditioning use. So determining your SRI value is a 2-step process. The roofing materials, solar reflectance, and thermal emittance are used to calculate that material surface temperature under conditions. And the SRI value for that material is determined utilizing a specific formula that compares the calculated temperature, surface temperature, with those of standard white material and a standard black material under the same specified conditions. Various factors will influence a material's solar reflectance and resulting calculated SRI value. As you see on the slide, there's some examples of solar reflectance and thermal emittance values that will result in a warmer or cooler roof. A black roof will have a lower solar reflectance and a higher thermal emittance. Metal roofs can have a higher solar reflectance, lower emittance, and white roof will have a very high reflectance and high emittance value, which will obviously result in your best cool roof option. I would like to note, though, that a cool roof doesn't necessarily have to be white. There are many cool color products which will use a darker color pigment that can be highly reflective in the near infrared, non-visible portion of the solar spectrum. So there are many benefits to cool roofing, as the ones I have outlined here. A cool roofing can improve your occupancy comfort by keeping your building cooler in the hot summer months, reduce spending by decreasing your total air conditioning use, also extending your appliances life, decrease your overall roof temperature, which can extend your roof service life by preventing premature polymer degradation through excessive heat and extreme thermal cycling, reduce your carbon emissions by decreasing fossil fuel generated electricity that's used for air conditioning, and also reduce the urban heat island effect, which occurs when the city is hotter than the surrounding rural areas due to dark surfaces like roofs and roads that absorb heat from the sun and have less shaded trees and vegetation. So lastly, a cool roof can also assist with local building code requirements that do have this cool roof, these cool roof requirements. As many previous presenters have mentioned, retrofitting and avoiding, in this case, avoiding a full roof tear off if possible is a great way to keep material out of the landfill. Roof restorations can add 10 to 20 plus years of life to your roof without contributing to the 600 million tons of construction and demolition debris that ends up in landfills annually. And if you restore your roof with strength and durability in mind, there's nothing greener than a roof that lasts. So torch applied roofing can be a good way to get at a potential roof restoration. With mineral surfacing, it provides some reflectance, keeping your roof cooler. It has minimal odor, so you don't have to shut down your facility, and it's quick to install. So there's no adhesive application and the labor is quicker. So it's also rain ready that same day. And here, this is an example of that application. This 62,500 square foot facility, Hologic, in Danbury, Connecticut. It's located in a hurricane prone zone and needed new corners and perimeters that were not adequately secured. And the roof was beginning to show signs of some aging. So the roof was removed to the deck in each corner and properly secured with some secure rock fasteners to meet FM requirements. That the current roof system was secured to the decking around that entire perimeter of the building. New insulation and a 2-ply mineral surface SBS bitumen system was installed in 10-foot wide sections. And this roof system would now meet and exceed the FM insured requirements for corner wind speed requirements, as well as it extended the life of the roof, getting it back under a long-term warranty. There are, many different types of roof surfacings that you'll see throughout these slides. In the previous slide, I referenced that a standard gray mineral surfacing over an SBS modified bitumen roof membrane. Here, I would like to expand on some of the new technologies that are in mineral surfacing, such as smog reducing minerals. The world is facing many global challenges, including air quality impacts on human health. Still, nearly 4 in 10 Americans currently live in counties with unhealthy levels of pollution. Since reducing air pollution remains critical to public health, there have been some new innovations in the roofing space to help mitigate these problems. Smog, which is nitrogen oxide, known as NOx, are made up of a group of gases, including nitric oxide and nitrogen dioxide, with nitrogen dioxide gas being more harmful to human health and the environment. Breathing in those compounds can trigger a variety of health problems and is a general issue if you're located near a heavily traveled road or live in an industrial area such as downtown Cleveland. These smog reducing granules are designed with a specialized photocatalytic coating that's applied to the base mineral, and it's activated by the sun's ultraviolet rays. So as the sunlight, as you'll see in this kind of the schematic, as the sunlight hits the roof containing these granules, free radicals are generated. The radicals then come in contact with the smog, which is nitrogen oxide and nitrogen dioxide gases, that will convert them to water-soluble nitrate ions, which are a more plant usable form of nitrogen, overall improving your air quality. The ion deposits will wash away over time, fully regenerating the surface to produce more free radicals and the capability to fight smog continuously. This smart solution for pollution mitigation can help communities contribute towards their nitrogen oxide reduction efforts and seamlessly be integrated into roofing materials to help remove smog pollution from the air we breathe. Photocatalytic materials have been used in construction for years, but not widely adopted in roofing materials. So if you think about the miles of roofing space available, these smog fighting minerals have the capacity to make a strong impact on the environment by improving the air quality for better human health. So here's another roof restoration option that's both for a single ply and a modified roof. This is a 2-part polyurea coating, which has 0 VOCs and is 100% solids. So a great no odor option to prioritize the health of your building occupants while also focusing on a highly durable, impact and UV resistant roof restoration system. As an example of how this product was used, the U.S. Department of Agriculture in College Station, Texas, had a thermoplastic polyolefin roof, a TPO roof, that was approximately 15,000 square feet. It was leaking, and during a roof inspection, rips and tears were found in the surfacing, and a thermal scan showed some areas of wet insulation. The building owner reached out and wanted a solution that would restore the roof's waterproofing with minimal disruption to the occupants. So the roof was cleaned and repaired in specific areas as needed, and this 2-part polyurea coating was applied by a squeegeing roller, and a fully reinforced polyester reinforcement was embedded in between. So it was, being a 2-part, it cured quickly to form a highly durable liquid applied roofing membrane to restore its water tightness for a highly durable and reflective roof surfacing. This is a new and novel technology to the roofing space. It involves restoring an older flood and gravel roof. If your building has a flood and gravel roof surfacing and you're looking to improve your building's efficiency, by having a white reflective cool roof option, you can look to utilize this technology. The application is relatively straightforward. Prepping and priming is the most important step to ensuring a long-lasting application. So you'll first spud off as much of the gravel as possible with wet vac, and the roof is cleaned to remove most of the dirt. A 2-part epoxy primer is applied to the roof to give a fresh surface to coat to. Then a silicone base coat is applied. That's the red portion in this photo. On the second photo, then it can be applied either by spray or roller application. It does require a very heavy base coat in order to go into all of those gravel crevices. Then a white silicone top coat is applied to the surface of that base coat to give you a white reflective roof surface. This solution can restore your flood and gravel roof, turning it into a more energy efficient building. Vegetative roofing brings to mind one of those all-around sustainable options. Although not a white roof, it has many of the attributes of a cool roof that I spoke about earlier, reducing the urban heat island effect and building in your building energy consumption. An additional major benefit of vegetative roofing is that that layer of soil media that absorbs the water like a sponge, it will capture the water when it rains, slowly releasing it through evaporation and plant use, or in larger rainstorms, it can slowly drain through that drainage system underneath the soil media, thus reducing the stormwater runoff. So if you imagine all the flat roofs in a city during a downpour, that water can overrun storm sewers, and green roofs can significantly reduce the amount of rainwater that would otherwise run off of an impermeable roof surface. It's however important to note that the roof structure must be able to support that load of vegetative materials under that fully saturated condition. All of the water that will soak into that soil media, you'll suddenly have a very heavy roof load. When it comes to vegetative roofing, maintenance can be a concern when looking at a vegetative roof, but there are many different kinds of green roofs that you can look to depending on how much maintenance you want to commit to. Commonly, Psidium and succulents, the alpine type plants, are chosen for green roofing. These plants will have a shorter root system that you're able to grow in less soil for slower growing and will result in less maintenance. If you're looking for a very visual roof, you might want to look to a more larger type flowers and plants that will only require more maintenance. But overall, it's a very functional use of your roof that's aesthetically appealing and shows your commitment to sustainability, where you can't necessarily see those zero VOC coatings and your recycled content that you would not necessarily see, but this could be a visual to the public. For my last slide, similar to the vegetative roof, if you have a roof space that you need to be more functional for your building occupants, but also has the benefits of a vegetative roof, you can make a sustainable roof solution to work for you. In this instance, there is a modified roof below for your longevity and resiliency, paired with a vegetative roof surfacing. As an example of how we utilized this was at the NYU Tisch Hospital roof. It's a smaller roof footprint, approximately only 2,000 square feet, but it needed a new roof due to its age, and it was starting to leak. So the owner reached out and wanted a long-term, durable yet sustainable solution. Obviously, because it was a hospital, the low odor finding a low odor solution was also very important. So we determined the ideal solution was a 2-ply modified bitumen roof for resiliency and redundancy. We installed pedestals and pavers around the perimeter for accessibility, and a green roof was installed in the middle, resulting in a functional and durable system that keeps your roof surfacing cooler. So you won't be running that HVAC system as frequently, reducing that urban heat island effect and also reducing the overall carbon footprint of the building. And similarly, the nice add-on for this roof is that it's sustainable, but also aesthetically pleasing for the patients in the hospital to view the roof outside of their windows. So thank you so much for your time. Appreciate it. And I'll be around at the end for questions. Thank you.
Thank you, Julie. Thanks. Great presentation. And we're going to turn it over to John. We're right on schedule. So John, I'm going to handle your slides.
Very good, thank you.
Yep, for some reason, everybody was having technical issues this morning. Bear with me 1 second. Can everyone see that? Okay, go ahead, John.
Okay, very good. Thank you very much for the opportunity of chatting with everyone today. I noticed when we signed in, there are several people on the call that I've worked with in the past and have been involved with using spray foam here in the Cleveland area. So with that, I'll go to the next slide, please. So my presentation today is going to cover 4 primary areas: the reasons for the increasing use of spray foam. That is going to be my primary topic. And then we're going to cover building code requirements, fire performance, environmental performance, rather briefly. Next. One of the primary reasons for the increasing use of spray foam is related to the energy code requirements. And next slide. So this is similar to some of the slides that David showed today. In fact, you'll see some other slides that are very similar because air leakage is one thing we're going to be concentrating on quite a bit today. But this is just a similar chart. This actually came from an article written by an architect, but it simply just shows the diminishing energy efficiency when you go to higher R values, so that with spray foam insulation being continuous, just 1 inch will reduce your heat transmission over 80%. And so as you go thicker, you have that diminishing return on investment. So while we are always, of course, interested in more use of spray foam, our primary thrust is to determine what's the best value. And as we'll talk a little bit more later, and David talked about as well, the real concentration, needs to be on air leakage. And essentially, the newer energy codes have pretty well topped out on R values, because they now see that adding just more and more insulation is not really cost effective. And so the effort now is towards concentrating on air leakage. Next. One of the most important aspects of the increasing use for spray foam is the increasing knowledge of building science. And Dave touched on this, and we'll talk about that now. Next. Essentially, a good building envelope is going to provide good HAM, and that just means the material needs to be a heat barrier, an air barrier, a water barrier, and a vapor barrier. And the good news is that the spray foam provides all these properties in one product. And so that makes the installation simpler, less trades involved, a better cost effectiveness. Next. This is similar to a couple of slides I think David showed. This is related to precast concrete or tilt-up construction, which is a very increasing application for spray foam. And the primary reason is dealing with this issue of condensation on the interior side of the precast. And I think, as David talked about a little bit, this is similar, where you get convective air currents going around or behind through the typical insulation materials, getting condensation on the back side. Next. So with spray foam being sprayed directly onto the substrate, in this case the precast, then you eliminate that cold surface of the precast, and you do not get the condensation. And so between stopping condensation and reducing air leakage, those are two primary reasons why spray foam is being increasingly used, not only on precast and tilt up, but a lot of different exterior substrates. Next. This is very similar to the chart that David showed, and essentially it's just showing kind of where that sweet spot is for insulation on exterior walls. And as you'll see here, where the graphs show the convergence, you're down with R values down in the neighborhood of 5. And in our industry, we have both open cell and closed cell foam, and the R values of closed cell foam can be over 7 per inch. So this kind of a chart can be met with 1 inch of foam. The open cell is typically 3.7 per inch. So it's extremely efficient at those thin sections. Next. So this is a chart that basically shows for certain climate zones tied in with the 2018 IECC, what the actual thickness is of some of the 2 different foams, both on roofs and walls, where you're factoring in now taking advantage of the air leakage. And just to take one example, closed cell foam generically has less than 1,000th of the air leakage as the ASHRAE codes require. So a half inch of closed cell foam basically provides a 99% air leakage barrier. So it's extremely effective as an air barrier. And the open cell foam, while it's not as effective, is still extremely good. So for instance, I'm sorry, if you could go back one, Cindy. No, no, you're going.
I'm sorry, John. Hang on 1 second. I don't know why it's advancing. Bear with me. I'm really sorry. Hang on.
That's okay.
Okay, here we go. There we go.
Okay,
Sorry.
okay. So if you just, I know it's just a little hard to read, but if you just say, take our climate zone in Cleveland, or zone 5, and you look at the, say, exterior wall with the closed cell foam, basically with a minimum thermal break, you're down to 2 inches of foam. Now, if you look at the prescriptive requirements, say for continuous insulation, which spray foam is, you might have to put in 4 to 5 inches of foam. So by taking advantage of the actual air leakage and factoring that in with the R value, you now can reduce the cost of the thickness of the foam, and therefore the cost of the foam, maybe 40%. So not only are you accomplishing the air leakage performance, you're actually getting the cost down of the spray foam that is basically competitive with any kind of insulation. So these are the primary reasons why spray foam is being increasingly specified. Okay, next. One of the other real benefits and why these tables are now starting to show how effective the spray foam is compared to other insulation materials is you have increasingly good software doing hygrothermal analysis. Next. And there's programs out, which many of the attendees have probably heard, called WFI. And basically, next slide. Basically, it's one of the programs where you can put into the program, say take a exterior wall assembly, you put into the assembly the typical materials you're planning to specify, the thicknesses, Woofy has a default section where you have properties of materials. You put that data into the software, and then it shows you on a video what happens to moisture movement within that wall assembly virtually every minute of the year. And this is a fabulous tool, and I really recommend that every architect utilize this, whether you do it in-house, you hire an outside firm like, say, Dave's firm, because there's two reasons. Number one, it helps you to optimize the wall assembly. There's a lot of discussion now about when are vapor retarders required. Sometimes a vapor retarder can actually be detrimental to an assembly. So the software programs like Woofy help you to optimize the specific design so that you don't specify too much of this or too less of that. So it's really in my opinion, a design tool. The second reason deals with liability. You know, if a building is constructed, as it turns out, there are problems with, you know, condensation, mold growth, whatever, in a wall assembly, then the question is going to be, why is that occurring? And when a design professional will be asked, what tools did you use to determine this design was going to perform? If you have actually conducted a Woofy example, then you have a basis. But if you have not used something that's state-of-the-art technology-wise, then you very well could be held accountable because you didn't really use the state-of-the-art knowledge. So I think these hygrothermal models, you know, are extremely important and quite frankly should be virtually used on every building. And once you get more involved in these, the costs are very minor compared to the you know, potential problems. Next. These are charts similar to what Dave showed, just showing in this case for precast where you have potential condensation on the interior side of the precast where the red marks, the red segments are of the graph. Next. And this is basically showing, you know, with spray foam, you eliminate all those issues concerned with dew point and condensation and mold growth. Next. I'll talk about a case history. I'm sure most of you here in the Cleveland area know the Cleveland Art Museum, and they had a major expansion quite a few years ago. It was done in 3 phases, and they brought in these precast exterior wall panels. They installed the wall panels in the first third of the expansion, first third phase. And after the first winter, they were getting condensation, you know, on the floor. And in art museums, that is a major problem. So we were called in to you know, assess the situation. Next slide, please. This is basically what the assembly was, the final decision that was made based on doing a hygrothermal analysis. And what had happened is they installed fiberglass insulation in that first phase, and through the higher humidity in the art museum, getting around and behind the insulation, the contractor did not seal the penetrations adequately. Then the moisture and the air got behind the insulation, condensed on the precast and went on the floor. And unfortunately, I think it was maybe a few weeks after they had the grand opening, they had to actually shut down the art museum for, I think it was several months to do the retrofit. And this was reported in the Plain Dealer, and it was quite a black eye for you know, the art museum and the specifiers at that time. Well, nevertheless, they had a Woofy conducted where they decided what they were the appropriate test conditions. This was the construction. These were the test conditions. Next. So basically, this was the result where they showed the dew point at the bottom curve and the actual temperature on the interior surface of the foam, so that there was no question whatsoever that the spray foam was going to be the proper solution. Next. Oh, I think you skipped one. So these were just some other parts of the analysis that were made, dealing with the moisture content, the potential mold potential. This is all the kind of information that a designer has access to make sure that the wall design is properly designed and constructed. Next. This is just a picture of the foam being sprayed in one area, and you can see these are the walls and everything else that were already installed in the first phase. So it was quite a challenge to go back in under that area that was already pretty well built out, and remove the drywall, take out the fiberglass, put the foam back in, put the framing back in. So these kinds of mistakes are very costly. Next. Simplified quality control. I don't have any other slides particularly on this item, but as I'm sure we're all aware, the availability and skills of the construction trades today are being downgraded quite a bit. Years ago, if you had a construction worker, for example, that was not doing quality work, then you basically dismissed him and you found a replacement. Well, today you can't do that. So as I go to job sites, I definitely see the quality of labor decreasing, because the important thing now for contractors is they just need some bodies there. They don't have a choice of getting the highest quality tradesmen. So they basically are retaining or hiring people that don't have the full skills or the commitment to quality work. Well, the beautiful thing about spray foam is because it is sprayed continuous, because you don't have to worry about seams, joints, et cetera, then you have much better quality control, on the job site. And some of the programs that are now available through the Air Barrier Association of America, the Spray Foam Association, we actually do third-party on-site inspections to verify that everything's been done correctly. And one of the other upcoming requirements in the energy codes is they're going to require third-party verification of materials that were installed properly to prevent air leakage. And as a result of that, when materials that are put up in sections with tapes, et cetera, and then you have third-party inspections, my prediction is you're going to have a lot more repairs made, higher costs, et cetera. So one of the real advantages of the spray foam is being continuous and having good quality control. And I guess I already covered the next one, dealing with more efficient labor productivity, other than to say that on a typical project, a two-man crew can spray typically 4,000 square feet of surface at 2-inch thickness in a shift. So there's no insulation systems that could come anywhere close to that. Well, what does that mean? That means you don't have the labor that you have to be concerned about. You have faster installation, quicker building completion time. You just have all these other advantages that have significant economic benefits. Next. So these are just a few examples of case histories. Some are in the Cleveland area, some aren't. This happens to be an ODOT building here in Cleveland, where they were having problems at the wall roof joint intersections. And so the solution there was to just spray that joint, with spray foam, and that, solved that air leakage problem at that intersection. Next. This is a swimming pool in Massillon. This was just basically a problem where, because of the moisture in the air, high humidity air getting around and behind the fiberglass, you got condensation, wetting of the fiberglass, this kind of a problem. So they took out the fiberglass, and is in the little circle area, they sprayed foam back. And I think there's just a couple of things that might be mentioned here as being important. One, what the solution was, and obviously doing this replacement turned out to be a very costly exercise, getting back to the cost effectiveness, but also, while you can't really see it very clearly, people don't realize how nice looking spray foam can be if you have the right materials, the right equipment, and the trained sprayers. We're involved in a lot of USDA inspected meat and processing facilities where they're inspected by USDA inspectors that are extremely critical about appearance, pinholes, roughness. So the spray foam can be sprayed to really look nice when necessary. Next. This is a office building down in Tennessee, actually, and they sprayed foam on all the walls and roofs. My company actually paid for a blower door testing for this building, and it performed beautifully. But the important thing is that half of this building was fully occupied by the contractor's staff. The other half was empty for future leasing. But the average monthly heating and cooling bills for this half of the building, which I think was about 8,000 square feet, was under $100 per month. I mean, that's less than most of us pay for our houses. So it just shows, with the proper design, the proper matching of the HVAC equipment with the spray foam, I mean, you can get those utility costs just extremely low. And this is the way that, we believe future buildings should be built. Next. This is a Williamsport, Pennsylvania hospital. Is a precast building. Next. The architect had originally specified a foam board insulation on the interior side. The general contractor, called my company saying, this foam board is going to be extremely expensive and difficult to install. In some places, it's not really that constructible. Do you think you could talk with the architect and get spray foam accepted as an alternate? So we did have that communication with the architect. He did change the specification. Here's the spray foam that was installed in that particular hospital. Next. So here's the economics. The specified system for this hospital with the foam board was $444,000. The installed cost, the subcontract price for the closed cell foam was $240,000. So you see some major cost advantages compared to boards of foam. And this is increasingly the case for tilt-up construction, where they'll typically put in 1.5 inches of foam board, and now that's moving more towards spray foam, again, for all the reasons that we've talked about, the productivity, the cost, the speed, etc. Next. Real quickly, the building code requirements across the United States have been very similar for foam. The foam must have certain flame spread and smoke requirements. They must be either be separated by 1/2-inch gypsum board or equivalent fireproofing, or the materials must pass full-scale fire tests with different types of fire protection services. Next. This happens to be one system that is actually the only foam in the United States that is now code compliant when left exposed. And this has dramatically reduced the cost and the simplicity of putting in a foam, as opposed to putting on various fireproofing materials, et cetera, et cetera. And so these materials can either be used by themselves, or they can be sprayed as a surface layer over regular foam, just depending on the requirements. Next.
Is that the end of your presentation, John?
No, I don't think so. So these are just some examples. This is a precast walls being done in a factory. This is a trend now too. And this is a case where they're spraying the yellow foam first, and then a gray foam as kind of the fire barrier protection as well. And that's now being done in the factory. Next. I won't spend too much time on lead credits, but the foam have EPDs, et cetera, qualify for a lot of lead credits. Next. And these are some of the projects in Cleveland that I'm sure most of you are familiar with. That ends the presentation.
Thanks, John.
Thank you.
Sorry I had trouble with your slides.
No problem. You did good.
Okay, let's move into Q&A. We've got an awful lot of questions here in the chat. So I'm going to start at the top. Sarah asks, does the closed cell spray foam insulation stud wall option still cause the same dew point within the mass masonry wall, which can result in freeze thaw issues over time? John, you want to take that one?
Well, I think Dave can comment on this as well. I think as far as new buildings, the spray foam can be used on CMU the same as precast. I think when you get into existing walls where the walls may have different facades, then that has to be looked at pretty carefully from a hygrothermal point of view.
Yeah, so to comment on that also, so it can, the short answer is yes, it can. And that's why we need to look through the hygrothermal modeling to make sure that the thickness or the R value that we're providing doesn't cause that issue. And it's predominantly with brick masonry. Older historic brick is much more porous, and so it can retain more water to it. And so what that analysis is looking for is what the critical degree of saturation is on that brick. And if we cross it, number one, and number two, do we actually have freeze thaw cycles? So we can assess the risk with that modeling to see if it's a good idea to insulate, and if it can be done, what do we have to limit our thickness to in that regard? We're working on what those critical degree of saturation numbers are. Through the research, there isn't a trending line that's really good, just because brick is not really homogeneous in its properties. One brick is completely different from the next one. But one good way to tell is if a building has a parapet, that brick is going to have a similar temperature gradient that it will if we introduce the foam. So if you notice that you have freeze thaw damage already up there, it's probably not a good candidate. If you're not seeing that, then it likely is.
I might add that I didn't mention that spray foam actually is installed on the exterior of sheathing in CMU, but the levels of difficulty in spraying it on the exterior, dealing with winds, overspray, the trend is to use the spray foam sprayed directly on the sheathing on the inside, bringing the studs inward, so you have that continuous insulation on the inside instead of the outside.
Thank you. Let's go on to Marcia's question. And John, I think you addressed this, but let's just hit it again. Spray foam and environmental flammability and toxicity issues. Can you just readdress that?
Well, in terms of the environmental issues, you have to look at the whole package in terms of any off-gassing vapors into the air with tied in with the energy efficiency. And so when you look at the total picture, you know, you basically find that the spray foams are quite environmentally friendly. And over the past few years, many states now are implementing mandatory requirements for more environmentally friendly chemicals, you know, within the spray foams industry. And virtually our entire industry is now introducing those products throughout the United States, not just in the states that require them.
Thank you, John. The next question, again, Dave addressed, but let's just go over the concern that spray foam shrinks over time.
There is some shrinkage in spray foam. It depends. The key is how it's installed. Meaning, just taking a typical example of a steel frame cavity. If you would just spray all the foam in that cavity immediately, you could actually get some shrinkage. But if you do what we call picture framing, where you spray the foam in a thin layer right around the studs first, where you get that shrinkage not in laterally but in thickness, then you kind of lock that foam in, and then you spray the balance, and then you have no shrink problems. So it's a matter of technique as far as how it's actually applied.
Thank you, John. Marcia asks, about 50% of carbon loss from buildings comes from small buildings like residential and small business structures. What efforts are being made to develop strategies to make the needed retrofits in our existing small building stock accessible to owners of such buildings who certainly don't have the expertise of this group? So hopefully the IRA will address some of that, but does our panel want to weigh in?
Well, I could take a quick shot at that, Cindy. We're getting very involved now in these state organizations that do weatherization for existing houses for lower income persons. And the national guidelines from the Department of Energy are highly recommending spray foam for a lot of applications. And that would be basement walls, you know, attics, you know, those types of applications. And so the spray foam is becoming now a very key part of these weatherization programs.
Thank you, John. Anyone else want to weigh in? I see Helen also put a comment there in the chat. Thank you, Helen.
Yeah, this is just a broader, I don't know if it addresses the actual question that they were asking about smaller buildings, but certainly with the new, I'm involved in the 2024 IECC development, the envelope requirements, and there's certainly more air leakage requirements for more buildings across more climate zones coming. So, you know, depending on how quickly Ohio adopts it, of course, but let's hope that some of those incentives drive that.
Yeah, and just to add to that, Ohio is a home rule state. So local jurisdictions can adopt other IECCs in lieu of what the state gives.
Great.
So is there some work going on with Cleveland to drive Cleveland to adopt a higher IECC 90.1 version? Or is this something that we could do together?
I'm not aware of them actually trying, but it could be something that this district or the folks on the call want to try to petition to too.
Yeah, and I can say that I'm part of a coalition of a number of organizations that we are in conversation with the city, trying to help the mayor's administration address environmental issues, particularly green building issues. Let's move on to George. I think your question was answered. Was this coding applied over the TPO? I think Dave and Julie both answered your question, George. Elaine asks, do we want to use cool roofing in our cool Ohio climate, or is warm roofing better for retaining heat?
Yeah, and I answered in the chat, but for the group, commonly in Ohio, we'll use more of a gray type surfacing. This will have a reflectance of around 28 to 30%, and that will enable the roof to reflect enough during those hotter summer months, but also in the winter provide a little bit of warmth as well.
And Julie, let's stay with you. Marcia asks about slate roofs, and I see you had a conversation there in the chat, but maybe for everyone, let's review.
Yeah, sure. So slate, it will primarily depend upon the color of the slate, similarly to the color that you would choose on a roof. The lighter colors will typically have a higher reflectance than the darker, but I would expect around a 30% reflectance as well.
Thank you. And there are a few questions in the chat that are coming directly to me about sharing this information. We're recording. It will be on our website under District Library, and all the slides will also be posted there. Helen asks, several jurisdictions that are developing policy incentives to drive higher performance buildings are providing grants, money programs for training for designers and installers, since they see this as a big gap in closing the performance gap. Sorry, that was from Helen.
I was more of a statement or a response to some of the conversation. Yeah, I mean, you can see in jurisdictions like New York, Pennsylvania, up in the Pacific Northwest, in outside of the US and BC, where they're really driving their codes to net zero. They're using some passive house tech as optional pathways, and other similar ways to stretch the envelope. They're recognizing that in order to do this, they've really got to close the gap on training and awareness, not just in the practitioners, but also in the installers. So they're actually creating funds to actually do that, to make sure that the code is actually implementable, and hopefully without unintended consequences due to poor installation, because things are getting more complicated. Testing is required. So yeah, they see that as a training gap and something that needs to be closed.
Thank you for clarifying, Helen. And Marcia comes back with what can the community do to better train and increase the committed workers in construction? And Dave, you responded, but can we expand on that?
Sure. I mean, I've had involvement with the International Masonry Institute, and I know that they have an excellent training program. They're, as well as other institutes locally, and the union shops locally have really good training programs. It's not so much the training as the actual people that they're struggling to actually get younger kids to want to do those trades. They're just not as sexy as college and whatnot right now that's being pushed. I think we need to have a shift in what's important.
Yeah, thanks, Dave. George asks, he's got a couple of things here. One of the issues with spray foam is making sure the application is uniform in thickness, which mostly depends on the person applying the foam. And then he goes on to say, recommendation for those using SPF when applying outside, make sure wind conditions are almost null. John, do you want to address that?
Well, no, I touched on that before. Yes, that's very important. The foam is a fairly fine mist, and it can drift significantly. So having minimum air when you're spraying outdoors is very, very important.
Is there a code restriction to using spray foam insulation on both the walls and the roof? And sorry, I'm reading these for the first time. Sorry, Dave did respond to that, but do we want to expand?
Well, the codes permit spray foam to be used in virtually every application. It's just a matter primarily of what the fire rating requirements are. And there's different requirements for roofs versus walls, of course. And spray foam is being used. It does have applications on the top of roofs as well. I mean, there's spray foam roofs in this country that have been in for over 40 years. And the key for the spray foam in the exterior roofs is the coating. You know, the coating has to be put on the right coating at the right thickness. And if that's done, then you have long-term performance. If you don't have the right coating and the right thickness, then you can have significant problems with spray foam on the exterior.
Thank you. Anand has a, Anand, I'm not sure if you're asking a question, only through tax abatements as incentives. We are still a minimum state despite being home rule state for energy codes.
Yeah, so Cindy, I was responding to a previous comment about being able to adopt higher IUCC codes. And I was just responding to that question. Or
Speak louder, please. Hard to hear you.
Yeah, I think Anand was saying he was just responding to some earlier comments. Thank you, Anand. Thank you,
yeah,
Martha.
I was just responding back to a question, Cindy, about can the city adopt higher IECC codes? And the answer is not unless we provide incentives, not through code. Because even though we are a home rule state, right? The state of Ohio is a min-max code state, unless somebody else differs.
Thank you, Anand.
Mm-hmm.
So Marcia is giving an example. I haven't been able to determine what the new Sherwin-Williams building is, even all electric, and the plain dealer architecture writers rarely comment on the environmental soundness. Does anyone have any information on the Sherwin-Williams building for Marcia? I don't, Marcia, sorry.
No, I don't.
Do we have any other questions from the audience? So one message that was directed to me privately, can we also discuss how to get owners and clients to commit to the technology needed to meet the goals? I think we've talked about this a little bit, but can we maybe open that up for a little more discussion? And I'll add to that. Do you all think that the IRA provisions will be as impactful as we all hope in terms of improving green building? Anyone want to start us off?
Oh, go ahead.
I mean, for me, I think doing things such as this is wonderful. I think education is extremely important. I think the more that building owners can educate themselves and learn more about the products and the for the IRA, and as much as we can get that information out, I think it can only help in really getting those green building codes up and to make things better. I think that's such a big thing. So I love participating in things like this to really help in that way as much as possible. I think education is key to a lot of that.
I mean, from my perspective, it looks like the provisions have made it easier to qualify for credits through the 179D provisions. So I'm hopeful. And, you know, the requirements are now down to 20, you have to show 25% more efficient than a baseline. And the baseline is based on a 90.1 standard that's 4 years old. So, you know, they've certainly reduced the minimum requirement for compliance. So I'm hopeful. And then the incentives for retrofitting existing buildings is looks pretty good too. But I think As Julie said, I think the building ownership needs to be educated that it's there and it can be used. So I think it'll be interesting to see how it plays out. I mean, there are also things in the IRA that I didn't mention for embodied carbon. So GSA has got tons of money to source low carbon materials. So we've been working with them on the glass side as they've been trying to set targets for what is low carbon material. So there's lots of other things in the IRA that may start to move the needle. I'm not sure that one in particular will move the needle on obviously operational carbon, but it's trying to attack both sides of the building sustainability picture.
The only thing I might add is that I'm kind of curious of what the federal government is doing when they review the various energy codes that the states have in place, because they do a review every so often, and it just seems to me that in addition to having the carrot through these tax incentives, that they ought to be taking a more stringent requirement that to correct for certain, qualify for certain funds, et cetera, the states need to adopt the newer energy codes. But I don't see a lot of activity in that regard, which I'm kind of surprised about.
Yeah, they did that some years ago. There was an incentive. You could only get some transportation dollars if you adopted the new energy code. But that was maybe even 10 years ago. I forget the bill that it was in. This year, they're pouring money into encouraging statewide adoption, as opposed to kind of saying you can't have it unless you do, unless you adopt.
Well, Ohio is one of the states that's really behind the curve energy code wise.
Right.
I think to build on also what Helen said about the Inflation Reduction Act and what Dave said before about that there's kind of like this missing pipeline of going into the trades. I think one thing that will help is while they've lowered kind of the bar to get the funding, they're also linking that funding to that, to get more, you can have to have apprentices on the project and things like that. So I think that will also hopefully help with some of like the workforce development challenges that we have now in the field.
And I'll close that conversation out by saying that Cleveland 2030 District did an education session strictly about the IRA, and that is available. That was recorded and is in our district library on our website with a local expert from Greater Cleveland Partnership, Courtney Kishbaugh. And we plan to do several other sessions throughout the year on the Inflation Reduction Act. So please keep watching our events calendar for those events as they come up. We're doing one in a couple of weeks that is strictly targeted to our museums and how they can access the opportunities in the IRA. So we'll be doing more on that as well. We're at 10 o'clock. I'd like to thank our panel very, very much. It was a very informative session. Really appreciate you taking time. Helen, particularly, she's on the West Coast, so she got up extra early this morning. I appreciate that, Helen. But all of you, thank you for a wonderful presentation. And I hope to see everyone at our next session in March. Thank you very much.
Thank you.
Thank you.
Thank you.
Have a nice day.